Now we're going to graph y equals cotangent x in a very similar way to how we graphed y equals tangent of x. What's the trig identity you remember about cotangent in terms of sines and cosines? So it's cosine over sine. And so we're going to have asymptotes here as well, right? Where, what x value makes sine 0? What's the first one that you usually think of? Sine of what equals 0?
0.
Sine of 0 equals 0, yeah. And then what's the next one? You know what a neat trick is?
Pi.
Yeah, pi, yes. You know what a neat trick is? If you have the graph of the sine function memorized, which you will eventually if you don't already, you can actually see where the x-intercepts are of the sine function. And that's where the sine's equal to 0, right? At the x-intercepts, the height value is 0. So you can actually see where it's equal to 0 visually if you have this graph in your head, which you will. And so, I mean, obviously it doesn't stop here, but the first non-negative one is 0. And then, oh, we know this value is pi, if this is just y equals sine x, that is. And then the next one is 2 pi, right? What's the next one? What would the one be over here? 3 pi. What would the one be over here if I continued the graph on like that? What would the one be over here? Negative pi, negative 1 pi if you like, right? This would be positive 1 pi. So what's the pattern? What kinds of values of pi? Just multiples of pi, right? Even and odds, right? Yeah, so that's going to be helpful. So that picture, if you have that picture in your head, you can figure things like that out rather quickly. Okay, so let's graph this thing. Again, we're just graphing one period, but when I state the domain and the range, I'm talking about the entire graph, right? Okay, so 3 values I'd like you to plot here. Not the same 3 as for tangent. A good one here, well, okay, we can't plot 0, can we? Because x equals 0 is actually an asymptote, isn't it? But what's the period of this thing? So I'm trying to indicate that's an asymptote. What's the period of this thing? What's the period? Pi. And as we've already noted, if you tried to plug in pi and take the sine of it, you get 0, you get division by 0, right? So there's an asymptote there as well. So just like before, I'm going to plot the 2 asymptotes. The y-axis is an asymptote. And the line x equals pi is an asymptote. Obviously there's a lot more, but I'm graphing just one period, and these are typically the 2 asymptotes we draw for one period. And then you're going to want to plot the value in between the asymptotes, this value, which would have to be what? Pi over 2, and then just split that value in half. Plot pi over 4, and then split the value between pi over 2 and pi in half. What would that be? 3 pi over 4. So those are the 3 values or kinds of values you want to plot here. This interval, the first interval represents 1/4 of the period, and then between 1/4 and 1/2, between 1/2 of the period and 3/4, between 3/4 and 1. So those are the kinds of values you want to plot. Okay, what's the cotangent of pi over 4? Well, what's the tangent of pi over 4? 1, so what's the cotangent? 1. Now, what's the cotangent of pi halves? Okay, use this if you're not sure, right? What's the sine of pi halves? It's 1, right? What's the cosine of pi halves? 0. So what's the cotangent of pi halves? 0 over 1 is just 0. So if you forget, you can get it. What about 3 pi over 4? Cotangent, rather, of 3 pi over 4?
-1.
It's going to turn out to be -1. Okay? And you can always verify that if you know your cosines and sines. You can always verify that by plugging into cosine x over sine x. Well, now, once you know that, it's not that hard to plot. Okay, we're going to have to go up to a height of 1, -1. Well, we go actually a lot further down than that, and a lot further up than +1, but those are the ones we're plotting. So pi force over pi force up 1. Pi halves is an x-intercept, right? Pi halves 0 is an x-intercept. 3 pi over 4 is at -1. And then you just use those points and the asymptotes as a guide, right? As you go to the left, does it look like the graph is going up? As you approach the y-axis from the left, it's going up. So if I draw it, as you go from the left the other way, it comes down. And it swings around in a nice smooth curve. It's not a straight line. And then it goes down as you go to the right. And if you want a more accurate graph, what can you always do? Plot more points. That's all your calculator does. Your calculator is not very smart. It's not artificially intelligent, right? All it does is plot points really quickly. So you are smarter than your calculator. Now, we know the period is pi. Now, let's think about the domain. Again, I'll use set builder notation, the set of all x such that it's assumed x is real, so we don't write that down. So we just write down the restrictions. So go back up. Well, I kind of erased the graph of the sine, but where are the x-intercepts of the sine function when you graph it? In other words, when is the sine function equal to 0, height-wise? At multiples of pi. We already saw that. So those are the values we actually have to restrict, because those are the values that make the denominator of cosine x over sine x 0. Cosine x over sine x is cotangent x. So though undefined, right? Can't divide by 0. So multiples of pi we restrict. So how do we write multiples of pi? X cannot equal multiples of pi. We just say x cannot equal k pi. Sorry, I had a 2 in there, and that's not right. It's k pi, where k equals an integer, right? What are integers? They're values like counting numbers, 1, 2, 3, 4, 5, blah, 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 but 0 and the opposite of the counting numbers, -1, -2, -3, blah, blah, blah. Make sense? Okay. About the range. Look at the graph. How low does it get? How high does it get? It goes all the way down, all the way up, and everything in between, right? Because it's a nice continuous graph. So it's probably, and I'm just, for convenience, I'm switching notations here. Interval notation, -infinity to infinity. So hopefully that doesn't throw you off, okay?